Mm. So in this session, we try to derive, differential equation for the differential equation of motion for the different types of mechanisms and motions. So this is the standard derivation we have already derived in the previous session. So here the component before this x is giving the angular velocity. So in the same way, for a given different types of motions and mechanisms, we try to derive the differential equations, and we compare that differential equation with this standard one. So here whatever we have as a multiplication of x would give the angular velocity of that particular system. And here in this case, for first of all we will consider the free vibrations, that is without damping, and slowly we incorporate the damping, and then further for the damped system we try to give externally excited forces. That means so far the vibration whichever these systems are executing, it's a free vibration in the sense we are not giving externally exciting force, but of course initially we are giving a small amount of perturbation, means a small amount of disturbance, so that it will disturbing its equilibrium position, and after that we are now not giving any further force. But whereas in the forcefully excited vibrations we are continuously providing the force for external force to excite the system. Aim is to derive these type of differential equations for the different types of mechanisms or motions. So how to derive those? There are so many methods. Generally we follow Newton's second law. Newton's second law. It's a very simple one. F equal to ma, where here a is acceleration given to the system because of the vibrations, and this F is the forces that are developed in the system. So we need to equate the forces developed in the system to the ma. Here the forces are causing the acceleration in this one. If this is the linear system, if it is a linear system, this is the one. And what if it is a rotational system? Of course we can write that also in the rotational system, that is momentum. In place of f we write a momentum equal to I into alpha equal to theta double dot in a rotational motion, clearly. And here m can be written as a f into l, and this is a f cross l. That means the length of the force, no distance from the momentum point to the force is always perpendicular. So we need to take that one, and by equating this one automatically we will find some differential equation. And apart from this one we also go for the energy method. So we have already discussed in the previous session that in an energy method, total energy equal to sum of the kinetic energy plus potential energy, which in turn is a constant always. And if you differentiate this one with respect to time, that will yield some differential equation. Why? Because this kinetic energy and potential energy are derived in terms of some variable x. So when you differentiate this total energy, automatically it will give some differential equation. And again we will compare that differential equation to this equation, and we will find out the omega. And apart from this one we have also virtual work method. Actually the general we don't go for this method unless otherwise it's clearly stated in the exam to solve the problem using the virtual work method. And because these two methods are much more easier to derive these differential equations than by using this virtual work. And we have one more method, that's a Lagrangian method. So Lagrangian method, it's also more like finding out the energies and differentiating those energies using the variables in the system. We will be having some special session on this Lagrangian method, system having a more number of degrees of freedom. I'm here. I said degree of freedom. So far I haven't mentioned that our variables also called as a degree of freedom. Why? Because Actually, number of variables is depending on the degree of freedom of the system. So for example, this is a simple spring and mass system. So in this case, what happening? I am disturbing this position like this. I'm just giving some force, and after that I'm stopping that force. So I'm giving initial perturbation. Means initially I'm just disturbing this mass so that it's a keep on executing some more to and fro motion, to and fro motion, and in how many directions it's making the motion? It's only in one direction. That's only if you take this as x direction, it's only making only in the x direction. That means its motion is only in x direction. That means its degree of freedom is 1. If it is not, if it is making motion more than one direction, for example even in the y direction also, then we need to consider two variables to represent the system. So in that case, what happened, degrees of freedom is 2, and the differential equation that we derive should be having the two variables. Here the degree of freedom of system is connected to the number of variables that they appear in the final differential equation. And now we will take up some of the examples. So this is a simple spring and mass system. So this is A represent the original initial position where we just hang some mass with the help of a spring attached to the top floor, and due to the mass there is an initial sag or extension in the spring. So because of that one, there is a initial and extension delta. But here in this case, this case B is a equilibrium position. Amount of the force produced in the spring is equal to the mg, because this is in a equilibrium position and there are no other forces acting on the system. And at this position, what I have given is I have given a initial displacement x in the downward direction. Because of this initial displacement, the mass has reached a position in such a way that the distance from the mass to the datum is x plus delta. And I would like to draw forces on the masses at this place. So this is the mass and m here. This is the m into x double dot, because this motion is causing acceleration to this mass, that is the m into x double dot, and mg is acting in the downward direction. And apart from that, we have a spring force in the upward direction, that is a k into x plus delta. So we have already seen f equal to m into a. Here a equal to x double dot. So m x double dot equal to forces we need to write here, and x in the downward direction. So while writing the forces, whichever force acts in the downward direction has taken as a positive, and the remaining forces that are acting in the upward direction will be taken in the negative direction. So here is spring force is acting in the reverse direction, upward direction, so that is a k into x plus delta, and then plus m into g. But at the equilibrium position, we have already seen k delta equal to mg. So here minus k delta plus mg would become 0, and we remain with k into x. So this will become x m into x plus k into equal to 0, and this can be written as x double dot plus k by m into x equal to 0. But the coefficient of the x is nothing but omega square. So omega equal to square root of k by m, and here there is no damping or no other forces in the system. That's why this omega is nothing but a free frequency of the system. If you go back and observe this equation, let's call this as equation 1. If I observe this equation here, the mg term and the k delta terms are missing. What I'm trying to say is the terms containing g and delta, static deflection, can be neglected while taking the final formula. But we need to remember that the g and delta cannot be neglected in each and every case. But here in this case, what happened? This force caused by the gravity is compensated by the initial displacement or static displacement produced in the spring. In some other cases, it may not be the case. That means the mass is not supported by the spring. So in that case, we cannot neglect G and delta. Now we will try to derive the same equation by using the energy formula. In the energy method, we know total energy equal to Ke plus Pe, and here Ke equal to the kinetic energy of the spring plus kinetic energy of the mass. But here kinetic energy of the spring is 0 because spring mass is neglected. So we have only kinetic energy of the mass. So that is half into m into x dot square and potential energy. So here, even though we are taken the ceiling here, but ground would be somewhere near to here. So when mass is moving nearer to ground, automatically its potential energy is decreasing. And in the same way, because of this movement, there is a strain energy developed in the spring. That is nothing but a potential energy. That's how we derived in the previous session also. But because of the stretching, this strain energy is increasing. So this potential energy. So this I have shown the potential energy here. This is the potential energy here. So this is a datum, and this is at a position delta plus x, and this spring potential energy is acting in this direction, and this potential energy is acting in this direction. Both are in the different direction, but which one is positive, which one is negative? Actually this is a negative. This is negative because it's a decreasing. Potential energy of the mass is decreasing because it's going nearer to the ground, but whereas it's a stretching, spring is a stretch, so it's a positive. So if I write in that manner, so potential energy for a spring, we know F half into K into x square. X is nothing but the change in length of the spring. So half into K into here, x is delta plus x. Delta plus x whole square minus potential energy of the mass. That is m into g into x plus delta. Here we know t equal to Ke plus Pe, and we need to differentiate. So dt by dt equal to 0. So when I differentiate this one, this term will become 2 by 2 m x double dot into x, and if I differentiate this term, plus 2 by 2 k x plus delta into x dot minus mg into x dot. So x dot is common in all the terms, so it will get cancelled, and here after cancelling this one, k into delta minus mg, that will become 0 because here in the equilibrium position mg equal to k delta. So if I write this equation again, this will become again derive the same equation as like in the Newton method. So here also, if you omega equal to k square root of k by m, and if you observe this equation also, here again the terms g, having g and delta are missing. That means we can here also we can neglect the g and delta terms in the final derivation of the while deriving the equation. Whenever the force produced by the gravity is compensated by the extension in the spring, then only we should neglect this one. And if the force generated by the gravity is not compensated by the spring force, then we should consider this one. We shouldn't neglect that one. Example, in this case, if I put this equal to 0 and g equal to 0, so automatically this whole term will become 0. Whole term will become 0, and here this will become half into k into x square. So when I differentiate this one, again we will end up with the same equation. So now question arises, so which method is better and which method we need to choose? So again, it's depending on the system complexity. So in the previous case, for example, if you don't know how to calculate potential energy of a spring, since we have already derived in the previous session, now you may feel that it's easier to calculate the potential energy of the spring. But in some scenarios, it may be possible that you may not be able to recollect. But whereas writing the simple forces is always easier. So if such a situation arises, it's always better to go for the Newton's method. But whereas if the finding out the forces, or if you don't know how many forces involved in a system, then it's better to go for the energy method. It's all depending on the convenient. Next example is horizontal bar. So this is the initial position, and this is mg. So as I already told in the previous session, whenever g is compensated by the initial initial extension in the springs, then we can neglect the g and initial delta terms in the equation. So I have given a small rotation. Actually this is rotating about the point O. It's a hinge to this one, this rod is, and the spring 1 is at a k1 at a distance of a, and this is at a distance of b. So when I given a small initial perturbation or displacement or rotation theta, so it came to this point. So it came to this point, that is causing some compression, and the spring came to this point, that is causing a extension. So this is compressed for, for a distance of x1, and this is extended for the for the value of x2, and initial displacement or the rotation that we are giving in these systems are very small, very small. So when this is very small, we can write here as a x1 equal to the distance from this point to this O, that is a into theta, that is L equal to r theta. It's a simply L equal to r theta. I mean, so in the same way, x2 equal to b into theta. So and f is acting in this direction, and here f2 also acting in this direction. This is in the, this is rotating. So I into theta, I into theta double dot, here I about O, because this is rotating about O. So I naught into theta double dot equal to f into L. So actually in this case, this is a rotating like this, this is rotating like this. So whatever rotating in the clockwise direction would be taken as a positive and remaining as a negative. So but if you take f1, this is a moving in this direction, anti-clockwise direction, so this is a minus f1 into at a distance of a, but f1 is nothing but k into x1. So k1 into x1 into a minus, even f2 also, f2 also in this direction, because it's opposing the extension, that is also k2 into x2 into b, but x1 equal to a into theta, and x2 equal to b into theta. So this can be written as I naught into theta double dot plus x1 is a, so k a square, k1 a square plus k2 b square into theta equal to 0. So it came into the standard form. Term before this theta gives the omega. Here omega equal to, here we straight away neglected g and delta. And if you don't want to neglect g and delta, here instead of x1, we should consider something like x1 plus delta 1. And here instead of x2, we should consider x2 plus delta 2. And we also should consider mg term, and automatically mg term with the delta 1 delta 2 will be compensated in the final equation. So in the energy method, ke, first of all, ke equal to ke of this dot, because the spring masses are neglected, this dot, so that is a half into I into omega square. Here what is the I? I is the moment of inertia about O, because it's rotating about this point. So this is rotating like this. So this is the kinetic energy and potential energy. While calculating potential energy, since force due to gravity would be compensated by the initial tension in the spring, so G and delta terms are neglected. That means PE equal to only potential energy of the springs. So that is half into K1 into x1 square plus half into k2 into x2 square, but x1 equal to a into theta and x2 equal to b into theta. So now dt by dt. So t equal to ke plus pe. So initially we differentiate this one. Omega equal to theta dot. So in place of this one, if we write this one by differentiating ke term, this is a 2 into 2 I omega. So differentiating theta dot square, that is a theta double dot into theta dot plus this term. In this term, x1 square means a square into theta square. So 2 by 2 k1 a square into theta dot plus again this also 2 by 2 k2 b square theta dot equal to 0. And if I simplify and rearrange again, it will give the same equation, theta equal to 0.